On For Science Salah Lotfy channel, we spotlight a breakthrough from the Egyptian Atomic Energy Authority, where scientists used gamma radiation to create a smart humidity sensor hydrogel. This innovative material is built from polysodium acrylate and poly-N-isopropylacrylamide, enhanced with calcium chloride and charcoal. It can absorb over 11 times its own weight in water vapor and shows remarkable thermal stability up to 450 degrees Celsius. Unlike traditional sensors, it's eco-friendly, lightweight and produced without chemical additives, using radiation alone to form a perfect cross-linked network. With potential uses in smart agriculture, climate control and industrial monitoring, this research opens the door to a new generation of sustainable humidity sensors. To explore the full details and scientific insights, watch the complete episode only on For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
In a world where smart materials are shaping the future of technology, few innovations bridge chemistry, physics, and environmental sensing as elegantly as this one. Today, on For Science Salah Lotfy channel, we explore a groundbreaking study that uses gamma radiation to create a novel humidity sensor hydrogel, a material that can feel moisture in the air and respond to it. Humidity sensing plays a crucial role in climate control, agriculture, storage systems, and industrial manufacturing. However, traditional sensors often rely on metallic or ceramic components that are expensive, energy-dependent, and prone to degradation. This research offers a new radiation-engineered alternative, a soft polymer-based hydrogel sensor that is superabsorbent, lightweight, and reusable. The research team developed an innovative composite hydrogel made from polysodium acrylate and poly-N-isopropylacrylamide, two well-known polymers recognized for their hydrophilic and temperature-responsive properties. By exposing this mixture to controlled doses of cobalt-60 gamma radiation, they achieved a perfect cross-linked network, forming a stable, interpenetrating structure without using chemical initiators or toxic catalysts. This technique not only ensures environmental safety, but also provides a clean single-step synthesis and sterilization process. To enhance the sensitivity, the scientists incorporated calcium chloride, CaCl2, and charcoal, both highly effective in absorbing and retaining water vapor. The result? A composite hydrogel capable of absorbing more than 11 times its own weight in water vapor and capturing over 2.6 grams of humidity per gram of material at 75% relative humidity and 35 degrees Celsius. This remarkable responsiveness positions it as an excellent candidate for next-generation humidity sensors in smart environments and atmospheric monitoring systems. Laboratory analyses confirmed exceptional improvements in water absorption and swellability, up to 244 times its dry weight, thermal stability, withstanding temperatures above 450 degrees C, enhanced porosity and surface area, confirmed by SEM micrographs, and superior humidity sensing performance, outperforming comparable hydrogels reported in global studies. These findings underline the scientific precision of using gamma radiation polymerization as a sustainable and scalable manufacturing route. From an economic and technological perspective, this research opens pathways toward cost-effective humidity sensors for diverse applications. From smart agriculture and environmental monitoring, to packaging, textiles, and energy systems that rely on precise moisture control. The ability to tune sensitivity by adjusting the radiation dose or filler content makes it adaptable to both industrial and household environments, all while maintaining an eco-friendly production process. This achievement highlights Egypt's leading role in radiation chemistry and polymer science, demonstrating how controlled radiation techniques can transform simple monomers into advanced smart materials with high economic and technological value. Stay tuned to For Science Salah Lotfy channel to discover more about how radiation technology is driving innovation, from environmental sensors to future-ready smart materials. Welcome to For Science Salah Lotfy channel. In this episode, we introduce a remarkable piece of Egyptian scientific innovation published in the Journal of Thermoplastic Composite Materials, Volume 38, Issue 11, in 2025, pages 4141 to 4162. The research is titled Gamma Radiation Synthesis of a Humidity Sensor Hydrogel, based on superabsorbent of polysodium acrylate and poly-N-isopropylacrylamide copolymer loaded with calcium chloride, CaCl2, and charcoal. It was conducted by Professor Dr. Mohammed El-Hadi from the Polymer Chemistry Department and Associate Professor Dr. Rayham Hussein Hilal from the Radiation Chemistry Department, both at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. The corresponding author is Professor Dr. Mohammed El-Hadi, whose contact appears as mohammedelhadi2000@yahoo.com. This study explores the powerful use of gamma radiation to synthesize a new type of humidity sensor hydrogel, a soft, smart material capable of sensing and responding to moisture in the environment. The research combines polysodium acrylate, a hydrophilic polymer that absorbs water, with poly-N-isopropylacrylamide, a temperature-responsive polymer. These two monomers are copolymerized through gamma irradiation, forming a strong, stable, and highly absorbent network, without the use of any chemical initiators or toxic catalysts. This radiation-induced method makes the process clean, safe, and environmentally friendly, while simultaneously sterilizing the final product. To enhance the sensor's performance, the hydrogel was loaded with calcium chloride, CaCl2, and charcoal. Calcium chloride acts as a hygroscopic agent. It strongly attracts and holds water molecules from the surrounding air. Charcoal contributes its porous structure and large surface area, increasing the hydrogel's ability to absorb humidity and improving its mechanical stability. Together, these fillers create a composite material that can absorb more than 11 times its own weight in water vapor and reach a swelling capacity of over 240 times its dry weight in water. The research team conducted a series of analytical tests to understand the properties of these hydrogels. FTIR spectroscopy confirmed the formation of new chemical bonds between the polymers and fillers. Scanning electron microscopy, SEM, revealed a porous, three-dimensional network ideal for water diffusion. Thermogravimetric analysis, TGA, demonstrated that the composite hydrogels can remain stable up to 450 degrees Celsius, proving their durability. The results showed that the inclusion of KCl2 and charcoal significantly improved thermal stability, humidity absorption, and vapor uptake compared to hydrogels made from pure polymers. The importance of this innovation extends far beyond the laboratory. By developing a radiation-engineered, eco-friendly humidity sensor, the researchers have created a material with broad industrial and environmental applications. It could be used in smart agriculture to monitor soil and air moisture, in storage and packaging systems to control humidity, and in climate control and electronic devices requiring precise environmental regulation. Economically, this approach offers a low-cost and scalable method to produce smart materials without relying on imported chemical agents, supporting both sustainability and technological independence. This research stands as another testament to Egypt's leadership in radiation chemistry and materials science. By combining polymer chemistry, radiation technology, and environmental innovation, Professor Dr. Mohammed El-Hadi and Associate Professor Dr. Rayham Hussein Halal have opened new doors for the practical use of smart hydrogels in modern technology. To learn more about the science behind this discovery and its potential impact on future technologies, stay with us here on For Science Salah Lotfy channel, where radiation chemistry meets innovation.
Welcome back to For Science Salah Lotfy channel. In this episode, we continue exploring a remarkable study published in the Journal of Thermoplastic Composite Materials, Volume 38, Issue 11, 2025. The research conducted by Professor Dr. Mohammed El-Hadi and Associate Professor Dr. Rayham Hussein Halal from the National Center for Radiation Research and Technology at the Egyptian Atomic Energy Authority, Cairo, focuses on the gamma radiation synthesis of a humidity sensor hydrogel. Today we move deeper into the experimental section, where chemistry meets precision, and every step reveals how advanced radiation techniques can transform simple monomers into a high-performance humidity-sensing material. The researchers began with carefully selected high-purity materials from international and local sources: N-isopropylacrylamide, NIPAM, supplied by Sigma Aldrich, USA, acrylic acid, 98% from Advent Chembio, India, and hydrous calcium chloride, CaCl2, from Wuhan Chemical Factory, China, and locally sourced charcoal and sodium hydroxide from El Gumhuria Co., Sofradas, and Sopodietsoxoster, Egypt. Each chemical played a crucial role in constructing the smart hydrogel matrix, a system designed to absorb water, sense humidity, and respond dynamically to environmental changes. The first step was preparing the sodium salt of acrylic acid, also known as sodium acrylate, SA. To achieve this, 9 grams of acrylic acid were dissolved in a solution containing 1 gram of sodium hydroxide in 9 milliliters of distilled water, stirred continuously at 50 degrees Celsius for 1 hour. This reaction neutralized the acid, producing the sodium acrylate, the hydrophilic component responsible for the material's high water absorption. Next, 1 gram of N-isopropylacrylamide, NIPAM, was dissolved in 9 milliliters of distilled water, then combined with the sodium acrylate solution under stirring at 35 degrees for 30 minutes. This mixture formed the SA-NIPAM pre-polymer solution, ready for irradiation. The resulting solution was cooled to room temperature and exposed to controlled gamma radiation, the key step that transforms liquid monomers into a solid cross-linked hydrogel network. The irradiation process was performed at the cobalt-60 cell within the Canadian Irradiation Facility at the National Center for Radiation Research and Technology, Cairo. The gamma dose rate was precisely maintained at 0.8 kg per hour, kgYH, allowing accurate control over the degree of cross-linking and molecular structure formation. Through this process, a copolymer hydrogel of polysodium acrylate-co-N-isopropylacrylamide was created, designated as H3 in the study. For comparison, pure hydrogels based on polysodium acrylate, H1, and poly-N-isopropylacrylamide, H2, were also synthesized under identical radiation conditions. To enhance sensitivity and functionality, the researchers prepared composite hydrogels by incorporating calcium chloride and charcoal as fillers. Before irradiation, 5 milliliters of the pre-polymer solution were placed in test tubes, and 1.5% or 3% of CaCl2 or charcoal was added separately. Upon exposure to gamma rays, these materials became integrated into the polymer matrix, creating new variants: H4 with calcium chloride, H5 with charcoal, H6 with both calcium chloride and charcoal combined. These compositions were then washed multiple times with ethanol and distilled water to remove residual chemicals, air-dried and oven-dried at 60 degrees Celsius until a constant weight was achieved. The result was a set of pure copolymer and composite hydrogels, each coded from H1 to H6 for subsequent testing and comparison. To evaluate their structural integrity and performance, the hydrogels underwent a series of characterization techniques that reveal both their microscopic and macroscopic properties. The first was the gel content test, which determines how much of the polymer has been successfully cross-linked by radiation. Each dry hydrogel sample was weighed, immersed in hot water at 80 degrees Celsius, extracted, dried again, and re-weighed. The gel fraction was calculated using the formula gel fraction percent W1, W0, x 100, where W0 is the original weight and W1 is the remaining weight after extraction. A higher gel fraction indicates a more stable, tightly cross-linked network. Next, the swelling degree, a critical factor for humidity sensing, was measured. Dry hydrogel samples were submerged in distilled water at room temperature for different time intervals. The swelling ratio was determined using swelling ratio, acrylate-co-N-isopropylacrylamide, WX, WD, WD, where WX is the swollen weight and WD the dry weight. These tests demonstrated how quickly and how much each hydrogel could absorb water, reflecting its responsiveness to moisture. The highest swelling behavior was observed in the composite containing both KCl2 and charcoal, H6, confirming its superior water interaction properties. The molecular structure and stability were then analyzed using several advanced techniques: FTIR spectroscopy, Fourier transform infrared, identified chemical bonds and confirmed the copolymerization between sodium acrylate and NiPAM. Scanning electron microscopy, SEM, revealed the porous, sponge-like morphology of the hydrogels, essential for water vapor transport. Thermogravimetric analysis, TGA, tested how the materials decomposed with heat, proving that the composite hydrogels retained stability up to 450 degrees Celsius. These observations provided solid evidence that the gamma radiation successfully enhanced both the chemical structure and thermal endurance of the materials. To examine their behavior as humidity sensors, moisture uptake and vapor absorption tests were performed. Samples were placed inside a custom-built humidity chamber containing a controlled fan, humidifier, and air purification system. Each sample, cut to uniform dimensions, was freeze-dried, weighed, and monitored as it absorbed moisture from the air. The moisture uptake ratio was determined using MT, MD, MD, where MT is the weight at a specific time, and MD is the dry mass. Further tests evaluated vapor water uptake by placing hydrogel discs over silica gel in a controlled chamber at 25 degrees Celsius and 50% relative humidity, tracking their weight increase over time. The results were striking. The composite hydrogel H6, containing both calcium chloride and charcoal, consistently outperformed all other formulations. It showed the highest swelling ratio, greatest water vapor uptake, and most efficient humidity absorption, confirming the synergistic effect of the two fillers. The presence of CaCl2 increased hydrophilicity and humidity sensitivity, while charcoal improved porosity and structural stability, creating a high-performance material ideal for sensing applications. Through this precise experimental design, the researchers successfully demonstrated how gamma radiation can be used to synthesize superabsorbent composite hydrogels with exceptional environmental responsiveness. Each step, from chemical preparation to irradiation, and from characterization to humidity testing, reveals how radiation chemistry enables clean, efficient, and scalable production of smart materials. This work stands as another proud achievement from Egypt's National Center for Radiation, Research and Technology, bridging polymer science with environmental innovation. Stay tuned to For Science Salah Lotfy channel as we continue to showcase how radiation-driven chemistry is powering the materials of the future. Cleanly, precisely, and sustainably.
Welcome to For Science Salah Lotfy channel. In this episode, we continue our journey into the fascinating world of radiation-synthesized humidity sensor hydrogels. Developed by Professor Dr. Mohammed El-Hadi and Associate Professor Dr. Reham Hussein Halal at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo. Today's episode focuses on the results and discussion, where data meets discovery, and the true scientific value of these gamma-irradiated hydrogels comes to life. Scene 1, Gel Content, the foundation of the network. The gel content represents the insoluble fraction of a cross-linked polymer network, the part that remains after all soluble components are removed. In simple terms, it tells us how tightly the polymer chains are connected. Too much cross-linking makes the structure rigid, reducing its ability to absorb water, while too little results in weak gels. Figure 1 shows that as the irradiation dose increases from 5 to 20 kilograms, the gel content rises sharply and stabilizes between 88% and 97.5%, depending on composition. The pure hydrogels H1 and H2 show the lowest gel fraction, while the composite hydrogel H6, loaded with both calcium chloride and charcoal, achieves the highest, almost 97.5%. This improvement results from the porous and hygroscopic nature of both CaCCl2 and charcoal. Their high surface area allows humidity and free radicals to diffuse through the polymer matrix during irradiation, enhancing cross-link formation. At the molecular level, gamma rays interact with both the polymer and water molecules, generating radicals such as HO and H. These radicals then combine with polymer chains to form new cross-linking points, building a strong three-dimensional network. The swelling ratio indicates how much water the hydrogel can absorb, and thus how responsive it is to humidity. All hydrogels were irradiated at 20 kilograms, and as shown in Figure 2, the swelling increased over time, reaching a maximum after about 30 minutes. The pure sodium acrylate hydrogel, H1, absorbed the least water due to its denser structure, while the copolymer hydrogel, H3, showed exceptional water uptake, approximately 263 times its dry weight. This behavior is linked to the formation of porous channels within the hydrogel that facilitate faster water diffusion. Hydrophilic groups and sodium ions within the polymer chains enhance the electrostatic repulsion of similar charges, expanding the network and allowing more water in. When CaCl2 and charcoal are introduced, the swelling increases further. H4, 172-fold H5, 194-fold H6, an impressive 244-fold of its dry weight. This extraordinary capacity highlights the role of both fillers. CaCl2 boosts hydrophilicity, while charcoal introduces porosity, creating a superabsorbent composite ideal for humidity sensing. Scene 3. FTIR spectroscopy, proof of chemical interaction. The FTIR analysis provides molecular fingerprints for each hydrogel type. Spectra revealed several key features. A broad band near 3441 cm1 corresponds to hydroxyl stretching, strongest in H1 due to high water absorption. The band at 1740 cm1 marks carbonyl stretching in pure PSA. Peaks near 2977 cm1 and 1545 cm1 identify the isopropyl and amide groups of PNPAM. In the copolymer hydrogel, H3, new absorption bands appeared around 1650 cm1, indicating hydrogen bonding between sodium acrylate and N-isopropylacrylamide chains, direct evidence of successful copolymerization. In the composite hydrogels H4, H5, and H6, peak shifts toward lower wave numbers confirmed strong interactions between polymer carboxyl groups and calcium ions or charcoal particles. This shift reflects new ionic and hydrogen bonds, proving that CaCl2 and charcoal are not merely additives but chemically integrated components of the polymer matrix. Scene 4. SEM morphology, the 3D structure revealed. Under the scanning electron microscope, all hydrogels showed porous, sponge-like structures, clear evidence of a three-dimensional network. These pores are critical. They act as microchannels for water movement and gas exchange. The pure PNI-PAM hydrogel, H2, appeared more compact, with smaller pores, while the pure PSA hydrogel, H1, had larger cavities. However, the copolymer hydrogel, H3, displayed the most balanced pore structure, uniform and well distributed. For H4, H5, and H6, the addition of CaCl2 and charcoal further increased porosity and surface roughness, improving both swelling and humidity response. These fillers bonded covalently with the hydrogel matrix, ensuring excellent interfacial compatibility and mechanical strength. Thermogravimetric analysis, TGA, examined how the hydrogels behave under rising temperatures up to 600 degrees. 3 distinct decomposition stages were identified. 1. Up to 350 degrees, evaporation of absorbed and bound water. 2. 350, 450 degrees, primary thermal degradation of polymer chains. 3. Above 450 degrees, slow decomposition of remaining carbonaceous residues. The thermal stability, based on maximum decomposition temperature, Tmax, follows this order. H6, 458.9 Tjax, H5 447.2 Dushaxi, H4 446.9 Dushaxi, H1 414.7 Dushaxi, H2 385.5 Dushaxi, H3 371.0 Dushaxi. These findings confirm that the presence of KCl2 in charcoal improves heat resistance by strengthening intermolecular bonding and reducing the rate of degradation. In practical terms, this means that H6 can operate effectively under demanding environmental conditions, ideal for industrial and electronic humidity sensors. The final test assessed vapor water uptake, a direct measure of how well each hydrogel responds to humidity in the air. As shown in Figure 6, the equilibrium vapor absorption ranked as H6, 1197 GeG, H5, 5.7 GeG, H4, 4.5 GeG, H3, 3.1 GeG, H1, 1.9 GeG, H2, 0.76 GeG. This ranking reveals a dramatic enhancement in H6, the composite containing both CaCl2 and charcoal. The combination of hygroscopic salt and porous carbon enables faster moisture capture and higher storage capacity, essential features for humidity sensing applications. By analyzing all these results together, a clear pattern emerges. Gamma irradiation successfully cross-linked the polymers into a stable, responsive network. The copolymerization of sodium acrylate with N-isopropylacrylamide optimized hydrophilicity and flexibility. The addition of calcium chloride and charcoal enhanced porosity, swelling, thermal stability, and humidity sensitivity. The result is a smart composite hydrogel, a material that reacts to moisture in real time, changes its structure accordingly, and maintains durability under heat and stress. These properties make it an excellent candidate for humidity sensors, environmental monitoring systems, and even smart packaging technologies. This research showcases how radiation chemistry can be harnessed to design and control material properties at the molecular level, cleanly and efficiently. From gel structure to thermal stability, every result confirms the power of gamma irradiation as a sustainable synthesis tool. This research showcases how radiation chemistry can be harnessed to design and control material properties at the molecular level, cleanly and efficiently. From gel structure to thermal stability, every result confirms the power of gamma irradiation as a sustainable synthesis tool. The composite hydrogel P-SA-co-N-isopropylacrylamide, CaCl2 charcoal, H6, stands out as a superior humidity-responsive material, paving the way for advanced applications in smart materials, engineering, and environmental technology. This achievement from the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, demonstrates Egypt's continued leadership in applying radiation science to develop solutions that are both scientifically advanced and industrially relevant. Thank you for joining us on 4Science Salah Lotfy channel. Stay with us as we continue to explore how radiation and polymer chemistry are reshaping the future of materials science, one discovery at a time. Welcome to 4Science Salah Lotfy channel. In this episode, we introduce a recent publication from the Journal of Thermoplastic Composite Materials, Volume 38, Issue 11, 2025. A groundbreaking study titled Gamma Radiation Synthesis of a Humidity Sensor Hydrogel based on superabsorbent of polysodium acrylate and poly-N-isopropylacrylamide copolymer loaded with calcium chloride and charcoal. This innovative research was conducted by Professor Dr. Mohammed El-Hadi from the Polymer Chemistry Department and Associate Professor Dr. Riham Hussein Halal from the Radiation Chemistry Department, both at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. The primary objective of this research was to fabricate highly hydrophilic composite hydrogels that could function as efficient humidity sensors. Hydrogels are fascinating materials, cross-linked polymer networks capable of absorbing water up to 100 times their dry weight without dissolving. They are commonly divided into three categories: synthetic, semi-synthetic, and natural hydrogels. Among these, synthetic hydrogels have captured scientific attention due to their tunability, mechanical strength, and higher water retention capacity compared to their natural counterparts. In this study, the team focused on two specific monomers, sodium acrylate, SA, and N-isopropylacrylamide, NIPA-AM. When exposed to gamma radiation, these monomers form an interpenetrating network copolymer hydrogel, a structure known for both superabsorbency and environmental responsiveness. What makes this synthesis remarkable is that it uses ionizing radiation instead of chemical initiators or cross-linkers. The radiation generates free radicals within the polymer chains, leading to controlled cross-linking and polymerization, all in a single, clean, and sterilized step. Gamma irradiation is a powerful, eco-friendly method for polymer modification. It allows scientists to fine-tune the structure, porosity, and sensitivity of materials without producing chemical residues. Unlike conventional chemical polymerization, this process is catalyst-free, energy-efficient, and environmentally safe. By using gamma rays, the researchers achieved a network structure that enhanced water absorption, thermal stability, and humidity sensitivity, making it suitable for real-world sensing applications. To further enhance the sensing ability, the hydrogels were loaded with calcium chloride, CaCl2, and charcoal. These additives serve distinct and complementary roles. Calcium chloride is a highly hygroscopic salt. It naturally attracts water vapor from the air, boosting the hydrogel's humidity responsiveness. Meanwhile, charcoal, or activated carbon, contributes a porous structure with an immense surface area, enabling the material to trap and hold water molecules efficiently. Together, these two fillers transform the hydrogel into a superabsorbent composite capable of responding to humidity changes with exceptional sensitivity and speed. The research team performed a complete characterization of the synthesized hydrogels using advanced analytical techniques. Gel content analysis to measure the degree of cross-linking, FTIR spectroscopy to confirm chemical bonding and structural changes, swelling tests to evaluate water absorption and retention, thermogravimetric analysis, TGA, to assess thermal stability, scanning electron microscopy, SEM, to study the internal morphology and pore formation, water vapor uptake and humidity absorption tests to determine performance under different environmental conditions. The results revealed striking improvements. The copolymer hydrogels, especially those containing CaCl2 and charcoal, displayed a higher degree of cross-linking, leading to enhanced gel fraction, swelling capacity, and vapor absorption compared to hydrogels made from pure monomers. The swelling ratio reached remarkable levels, showing that the hydrogels could absorb and hold vast amounts of water, up to hundreds of times their dry weight. Moreover, the thermal stability improved significantly, allowing the material to maintain structural integrity even at elevated temperatures. Most importantly, the humidity absorption increased dramatically, positioning these hydrogels as next-generation materials for humidity sensing and environmental monitoring. The scientific impact of this study extends into several practical domains. Hydrogels like these can be utilized in smart agriculture, helping monitor soil and atmospheric moisture with high precision. In packaging industries, they can protect moisture-sensitive goods, electronics, and pharmaceuticals. In environmental systems, they can regulate and track humidity levels in controlled spaces such as laboratories, storage units, and greenhouses. From a technological and economic perspective, the method offers low production cost, high scalability, and environmental safety, key factors for commercial and industrial deployment. The study also demonstrates how radiation chemistry can be used not only for polymer synthesis, but also for the design of smart, responsive materials. By adjusting the gamma irradiation dose, scientists can fine-tune the gel fraction, cross-linking density, and sensitivity, tailoring the hydrogel's behavior to match specific humidity or temperature ranges. This flexibility allows the same base material to serve in multiple applications, from medical and environmental sensors to energy storage and water harvesting systems. This research represents yet another achievement from Egypt's National Center for Radiation Research and Technology, part of the Egyptian Atomic Energy Authority. It highlights how radiation polymerization can transform simple organic monomers into smart, functional materials with immense industrial and environmental value. The collaboration between Professor Dr. Mohammed El-Hadi and Associate Professor Dr. Reham Hussein Halal reflects a growing commitment to applying radiation science for sustainable technological innovation. In summary, this research successfully demonstrates how gamma radiation can be used to fabricate superabsorbent composite hydrogels that function as efficient humidity sensors. Materials that are cleanly produced, highly stable, and economically viable. By combining radiation chemistry, polymer science, and environmental technology, this study paves the way towards smarter materials for a sustainable future. Stay tuned with us here on For Science Salah Lotfy channel, where science, innovation, and radiation technology meet to shape tomorrow's discoveries. Welcome to For Science Salah Lotfy channel. In this segment, we continue exploring the groundbreaking research conducted by Professor Dr. Mohammed El-Hadi and Associate Professor Dr. Reham Hussein Halal from the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo. Focus on the final stage of their study, the humidity absorption behavior and practical sensing performance of the newly developed composite hydrogel synthesized by gamma radiation polymerization. The results revealed that hydrogels based on copolymers, those combining sodium acrylate and N-isopropylacrylamide, showed higher vapor water uptake than hydrogels made from pure monomers. This high vapor absorption expands the surface area and enhances the hydrogel's capacity to hold moisture, especially in the composite sample H6, which includes calcium chloride and charcoal. Both materials act as deliquescent agents, substances that naturally absorb moisture from the air and form a liquid solution. When exposed to humid air, calcium chloride begins to dissolve as it captures water molecules. This phenomenon, known as deliquescence, is key to the hydrogel's remarkable performance as a humidity sensor. A unique feature of this material is the thermosensitive behavior of P-NiPM, short for poly-N-isopropylacrylamide. At temperatures below 40 degrees C, the hydrogel remains hydrophilic, absorbing water through hydrogen bonding between its amide groups and water molecules. However, when the temperature rises above 40 degrees, the hydrogel shifts to a hydrophobic state, repelling water and shrinking as the polymer chains collapse. This reversible mechanism is controlled by two molecular forces: hydrogen bonding, which attracts and holds water molecules, and hydrophobic interactions, driven by isopropyl groups, CH, CH3, that push water out. In the study, this behavior was observed clearly in the pure P-NiPM sample, H2, and also in the copolymer, H3. Yet in H6, the presence of charcoal and calcium chloride overcame this limitation, maintaining strong moisture absorption even at varying temperatures. To measure humidity absorption, all hydrogel samples, from H1 to H6, were tested at a constant temperature of 35 degrees C and relative humidity of 75%. Each sample was placed on a glass petri dish to equilibrate and absorb moisture from the surrounding air. The results were impressive. H1 absorbed 0.31 grams of water per gram of hydrogel, H2 absorbed 0.186 grams, H3 reached 0.477 grams, H4 and H5, which contained KaCl2 and charcoal individually, absorbed 1.33 and 1.75 grams respectively, and finally, H6, containing both CaCl2 and charcoal, absorbed an outstanding 2.63 grams of humidity per gram of material. This superior performance is attributed to the synergistic effect of both fillers. Calcium chloride provides chemical absorption of water vapor, while charcoal contributes physical adsorption due to its large surface area and porous structure. The research team also evaluated how temperature affects the moisture absorption capacity of H6. At lower temperatures, below 30 degrees C, the hydrogel exhibited a gradual increase in absorption with humidity. But once the relative humidity exceeded 40%, water uptake rose sharply, reaching its maximum near 40 degrees Celsius. Beyond that point, as the temperature increased, the material transitioned from hydrophilic to hydrophobic, leading to a slower rate of absorption. This unique behavior demonstrates that the humidity sensing mechanism can be tuned by temperature, making H6 a smart material capable of adapting to environmental changes. Unlike conventional hydrogels that swell excessively in water, this composite remains dimensionally stable, a critical property for sensor applications. When compared to previously reported humidity sensors, the H6 composite hydrogel clearly outperformed them in both humidity absorption capacity and water swelling efficiency. At 35 degrees C and 75% relative humidity, H6 achieved 2.63 grams of humidity absorption per gram, while most reported sensors ranged between 1.7 and 2.4 grams. In water absorption tests, it reached 244 times its dry weight, surpassing all earlier designs. This combination of fast response, high capacity, and stable recovery demonstrates that gamma radiation synthesized hydrogels can compete with, and even outperform, chemically polymerized systems. In conclusion, the research confirmed that the copolymer hydrogels with calcium chloride and charcoal achieved the best performance in swelling, thermal stability, and humidity absorption. The gel fraction depends directly on both the irradiation dose and the chemical composition. The composite hydrogel H6 can effectively act as a moisture-sensitive material, suitable for constructing next-generation humidity sensors. This work marks another scientific milestone from the National Center for Radiation Research and Technology, part of the Egyptian Atomic Energy Authority. By combining radiation chemistry with polymer science, Professor Dr. Mohammed El-Hadi and Associate Professor Dr. Reham Hussein Hilal have created a material that is smart, sustainable, and highly functional. Hydrogels that sense humidity, powered by gamma radiation, could soon become vital components in smart agriculture, environmental monitoring, and packaging technologies. Thank you for watching this scientific insight here on For Science Salah Lotfy channel. Stay tuned as we continue to uncover how radiation-driven materials are shaping the technologies of tomorrow.
As we reach the end of this scientific episode here on For Science Salah Lotfy channel, I would like to take a moment to express my deepest appreciation to the distinguished researchers behind this remarkable study. This work reflects the true spirit of scientific innovation, combining the precision of radiation chemistry with the creativity of polymer science, all achieved within Egypt's leading Center for Advanced Materials Research. My heartfelt gratitude goes to Professor Dr. Mohammed El-Hadi from the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt, and to Associate Professor Dr. Reham Hussein Hilal from the Radiation Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Your outstanding effort and dedication have resulted in research that not only advances scientific understanding, but also opens real pathways towards smart and sustainable materials for the future.
On behalf of For Science Salah Lotfy channel, I, Professor Dr. Salah Lotfy from the Egyptian Atomic Energy Authority, extend my sincere thanks and appreciation to both of you for your exceptional contribution to science and innovation. Your work stands as a shining example of how Egyptian researchers continue to lead in the field of radiation applications and polymer technology.
And to all our viewers, thank you for following this scientific journey. I invite you to share your thoughts and comments about this fascinating research in the discussion section below the video. Your feedback and questions are always welcome and help us keep the conversation of science alive. Stay curious, stay inspired, and see you in the next discovery, right here on For Science Salah Lotfy channel.